Hello everyone, welcome to GATE Wallah and welcome to GATE Wallah Aerospace. So guys, GATE Wallah has started coaching for aerospace engineering students, those who want to appear for GATE Aerospace Engineering. So GATE Wallah has already launched courses, and this series, which is the YouTube series, is regarding some of the important topics that we see in the propulsion in the aerospace. And guys, I'm going to teach you all propulsion in your coaching. Okay, so guys, in the last lecture, we had discussed about the thrust equation, which is which is required for generating thrust in case of all the aircrafts. So we have discussed about one thrust equation that we have seen, which is a generalized equation for any of the vehicle which moves due to the impact of the velocity and pressure thrust. So today we are going to move ahead from that equation. We are going to use that equation to calculate what are the thrusts which are developed in different types of vehicles. And then we will see the propulsive efficiency. So whenever we develop the thrust, at that time we have to see what is the efficiency with which the thrust is being generated. So we are going to see what happens to the propulsive efficiency. Okay. So before moving on, let me introduce you to myself. Guys, my name is Vinod Kumar Datusliya, All India Rank 1 in GATE. I have done my MTech from Aerospace Engineering in ISC Bangalore. And I have worked in General Electric, where I have designed aircraft engines. And guys, I'm going to teach you all the propulsion engineering, or the propulsion, the chapter of propulsion in aerospace engineering. Okay, so this is the fifth lecture that we are taking in this series, and today we are going to discuss about the propulsive efficiency. But before discussing about the propulsive efficiency, let's take back a little bit from the last lecture and then discuss onto that. So last lecture we had seen the thrust equation. Okay, so in the thrust equation, if you all remember, we had discussed that the thrust developed by any aircraft consists of two terms. So thrust was there was a term which was coming from the change in momentum of the gases. So mass flow rate of air plus mass flow rate of fuel, they both are exiting with velocity v exit, and then the air is getting inside mass flow rate of air at velocity v infinity. This is the term which was coming from the change of momentum. In last lecture we had seen Newton's second law and Newton's third law. Okay, and then there is one more term which comes from the pressure term, that is P exit minus P infinity multiplied by area of exit. These were the two terms which we had discussed. So today we are going to go ahead and we are going to see what are the different types of aircraft that we have in real life, and how the thrust is developed, or how the thrust actually looks for them. So to start with, first of all, we are going to discuss the first. Just hold on a second. Okay, so first we are going to see the first aircraft, that is called as the turbofan. Sorry, turboprop. So if you see this type of aircraft, very smaller size of aircraft generally that you see are turbopropeller. Now, what do you mean by turbopropeller? So when we talk about a turboprop, generally turboprop means turbo plus prop. What is turbo? Turbo is the turbine engine and prop is the propeller. So turbine will generate the power to drive the propeller, and propeller will drive the aircraft by generating thrust. So what happens is here is a turbine engine which runs on Brayton cycle. So there will be compressor, there will be combustor, there will be turbine, and there will be smaller exhaust as well. Okay, so this is the turbine engine which generates your total power, and that power is fed to the propeller with the help of a gearbox. Generally, the turbine engines, they run at very high RPM. So if we talk about simple two-spool engines where turbine drives compressor and there is a LP turbine which drives the propeller, generally they run at a speed of somewhere around 3000 RPMs. But if you see the propellers, they cannot run at such a high RPMs. The RPM for these turboprops should be much lesser, in the range of 400 to 500, where they produce the maximum efficiency. So the turbine RPM, which is around 3000, 2800, 3000, whatever in that range, that has to be reduced down to 400 with help of a gearbox. So that is what is actually the use of gearbox. So now the propeller is running. So how the thrust is generated? So you see, what is the purpose of a propeller over here is when the propeller runs. So let's say this is the propeller which is there, and this propeller is having blades like this. So when there is a power which is provided to this propeller, so you are providing certain power. So this is the power that you are providing. And when you provide this power, the propeller actually moves. And when it is moving, you see that it will suck in certain amount of air. So let's say it sucks in mass of air m dot a. Okay? And the velocity with which it is sucking air is again v infinity. Okay, and when the gases are going out, or when the air is going out, again it will be moving with a velocity which is slightly higher, or maybe a little more higher. We will see how does the velocities look like. So this will be moving with again the velocity v exit. Okay, and from here you can see that the thrust developed over here would be equal to, so here there is no mass flow rate of fuel, it is the only the change in momentum of the air. Okay, so the thrust generated would be mass flow rate of air multiplied by v exit minus v infinity. That is what is the basic equation that we see in the propeller. Is it clear? So this is mota moti the thrust which is developed. So guys, if you see in a turboprop engine, there will be a slight thrust which will be coming from this exhaust nozzle also. But that thrust is very small, because the amount of air which actually passes through this turbine is very low as compared to the air which passes through the propeller. Though we can calculate this thrust, so again for calculating the thrust over here, you have to take mass flow rate of air which is going through this route. Okay, and then you have to see what is the exit velocity coming over here, what is the velocity with which the aircraft is moving. This is what is the thrust. So you will have one more component from here, and a major component which will be coming from here. Okay, so this is somewhat the basic turboprop engine. So now let's move to a much complex variant of this turboprop. So you see, these turboprops are really good good engines, but they have a problem of having lesser efficiency whenever the tip speed reaches Mach number 1. Okay, so whenever the speed of the propeller tip becomes sonic, in that region they lose very high efficiency. Okay, so we are going to see that how does the efficiency look like as whenever the aircraft is moving close to the Mach numbers. Okay, so that we are going to see in coming slides. But first we will see that what do we actually do to improve to retain this efficiency at a much higher domain, at a much higher range of Mach numbers. So what we actually do is we design an engine which is called as turbofan. Okay, so turbofan engines are same like the turbopropeller. So you see that there will be a turbine engine that will be directly coupling a fan. Okay, and you see there is a cowl which is placed on top of these fans. Okay, there is a cowl which is placed over here. Generally this is a much smaller cowl, but in the real life you see the cowls also have a somewhat like this. They have a somewhat like this range, and the exit would be somewhat like this. Okay, so what happens is, you see over here the air is going, and when it is coming out, it is coming out in the form of a nozzle, such that the velocity of air which is coming from here is around sonic. Okay, so we will see when we will be discussing the turbofans in a much detail. At that time, we will see why the velocity reaches sonic over here, or why do we want the velocity to reach sonic over here. But for the simplicity, we are going to discuss only like the turboprop. So if you see over here, in case of a turbo fan engine also, there will be a mass of air which will be coming over here. So mass flow rate of air, it will be coming. It will be moving with velocity v infinity, and when it exits the fan, it moves out with a velocity v exit. Okay, and you see again, we can calculate how much is the thrust generated. So if you see, the thrust generated would be again similar to the turboprop, mass flow rate of air multiplied by v exit minus v infinity. This is the thrust from fan. Okay, this is the fan thrust. Okay, now again I told you that if you want to write the equation or the thrust from the jet, which is slightly very low, in the range of 10 to 15% of the thrust, but if you want to write, you can also write plus the thrust from mass flow rate of air through turbine multiplied by v exit turbine minus v infinity, ठीक है, plus p exit minus P infinity into area exit. So this is what is the thrust, second thrust equation, which you will see coming from the turbine. Okay, so turbine engine thrust. Okay, but you see, this quantity will be very, very less. Generally, this quantity becomes very dominant in case of a turbojet engines. Okay, so this is a turbo fan engine. This turbo fan thrust is mostly maximum. Okay, and this is a small, very small quantity. Okay, generally we will see that the propulsive efficiency in case of a fan would be much higher as compared to the jet thrust. So we are going to see what happens to the propulsive efficiency. Then you will be able to realize why the fans are preferred as compared to the turbojet. Okay, so this becomes the thrust for a turbo fan engine. Now let's go to the third variant. So before going to the jet, let's say let's go to turbojet engine. Okay, so in case of a turbojet engine, though we have already discussed in the last class, we have seen that turbojet engines are almost the same. Okay, and what you have is, you have your compressor over here. There will be a series of compressor blades. Okay, this will be your compressor. We will see that these are the actual type of compressors. We will study later. Okay, then you have a combustor. Okay, you have a region where actually the combustion happens, and when the gases are coming out of the combustor, they will be directed to turbines. Okay, so there will be a series of blades over here. So they will be directed to 2 or 3 stages of turbine, and finally the jet will be going out. Okay, and now if you see supersonic jets, they will have afterburner. They will have a lot more of complexities, but this is a simple jet engine that we are seeing. So if you see a turbojet engine, there will be mass flow rate of air coming in at velocity v infinity. There will be mass flow rate a plus m dot f, which will be going out. It will be going out at velocity ve. Okay, and this is what is the thrust equation that we have developed. So the thrust in this case would be equal to mass flow rate of air plus mass flow rate of fuel multiplied by v exit minus mass flow rate of air multiplied by v infinity plus p exit minus p infinity into area exit. Okay, so this is what is the basic typical equation that we have derived. This equation is valid for almost all the vehicles in slightly modified form. So everywhere we have to modify it. Okay, so I'm sure you guys might have understood how does a thrust of a turbofan looks like, turboprop looks like, turbojet look like. Now we will go to the last, that is last type of vehicles, which are called as rockets. So guys, rockets are very special case. Rockets, if you see the rocket engines or the missiles, everything that does not require air, atmospheric air to breathe in. So if you see these turbojets engine, they take air from the atmosphere. They take air from atmosphere, they process it, and then they send it out. And in return, they get thrust. But in case of a rockets carry their fuel and oxidizer both together. So they don't require any air. Okay, they develop thrust on their own. That is the reason why these rockets are also used in space, outer space, where there is no oxygen present. Okay, so how do they develop the thrust? So what they have is they have an oxidizer, they have a propellant, okay, fuel. So let's say this is oxidizer and this is fuel. What they do is they combine oxidizer and fuel in a combustion chamber. So this is, let's say, this is generally not a combustion chamber. This is slightly different variant. So you see the burning happens over here only. So this is the region where actually the oxidizer and fuel mix and they generate very high pressures. Again, this high pressure propagates over here, and while passing through the nozzle and going out. So you have ambient over here, P infinity you have over here, and you see this is very low pressure. So when they passes through convergent divergent nozzle, in the first class we had seen the nozzles. So you see this is a sort of convergent divergent nozzle. This is what is convergent divergent nozzle, whatever I have drawn in pink. Okay, so you see your fluid enters over here, it accelerates, and again further it accelerates. Okay, so now if you see, let's say this propeller is over here, it is lying at a stagnant velocity, and when it is coming out, it exits with a velocity v exit. Okay, so now you see if we want to write the thrust equation for a rocket. So thrust for a rocket, you see thrust for a rocket would be equal to, so now you do not have any mass flow rate of air. So you have only mass flow rate of fuel. So you have mass flow rate of fuel multiplied by, or not fuel, you can say mass flow rate of mixture. So mass flow rate of gases multiplied by V exit, where m dot g is the amount of gases which is coming out. M dot g is the amount of gases. It is amount of gases coming out of engine. Okay, so which consists of mass flow rate of fuel plus mass flow rate of oxidizer. So this is mass flow rate of fuel plus mass flow rate of oxidizer both. Okay, so mass flow rate of fuel plus mass flow rate of oxidizer into V infinity. Now the second term, that is mass flow rate of air multiplied by V infinity, that will not be there. Okay, so this will be the thrust, plus here you have P exit minus P infinity multiplied by area exit. This component will also be there. Okay, and you see this component varies significantly. Okay, this component could be as high as 20 to 30% in case of rockets also. So you see when the rockets are flying at normal atmospheric condition, this P infinity will be P ambient. But as we go into the space, this quantity will be dropping, and in outer space, it will almost become 0. So this component can be a significant contribution into the thrust when the rocket is moving. So while designing, we generally take this component also into the consideration. Can be significant, okay, in the order of around 20 to 30% of total thrust. Okay, so this is what is called as the thrust in case of a rocket. I am sure most of you might have seen this, seen these equations. Okay, you might have looked these equation in college or in your degree also. Okay, so now let's once we have seen all the thrust equations, now let's discuss what is the efficiency of a engine. Okay, so when we talk about efficiency, there are two types of efficiency. So if you see the turbojet engine has two type of things. One is the Brayton cycle. So you see, when you burn fuel, you burn mass flow rate of fuel, and you have certain calorific value of the fuel. So the energy released would be mass flow rate into CV. This energy would be converted by your Brayton cycle. When you give this to Brayton cycle, it will give you power. ठीक है, and power would be equal to efficiency of Brayton multiplied by the heat supplied. Heat supplied would be equal to mass flow rate into CV. Okay, so you see that the power which is coming out will already be accounting certain losses which will be happening over here. Okay, so now certain power is developed. Now this power is transferred to either fan, or it is transferred to propeller, or it is transferred in case of jet. Okay, so now we need to see what is the efficiency with which this power is converted into thrust, because power, whatever the power developed, will not be equal to thrust power. Whatever the power that your engine is developed will not be equal to the thrust power. Why do we say so? Okay, so to understand this, first calculate what is the thrust power that is present in the engine. So what is thrust power? Thrust power is nothing but it is the power that has been converted, or that is present or available with the aircraft. So you see, if there is an object which is moving with a velocity v, and on this object if a force is applied F, so can anybody tell me what is the energy that we are imparting to this vehicle per second? What will be the power that you will be imparting? So I'm sure in your early years in 11th or 12th class, you might have seen that the power in case of a force acting on a body will be equal to force multiplied by velocity of the vehicle. Is it clear? I hope everybody have seen this. Power is equal to force multiplied by velocity. So if there is a force applied on the object, okay, and its velocity is v, the power that you are providing, instantaneous power that you are providing, is force multiplied by velocity. Is it clear? So now let's say if you have a vehicle, if you have aircraft, so let's say this is an aircraft. Okay, and this aircraft is developing certain power. Okay, and that power, whatever is the power available to the aircraft, will depend on what is the force which is acting on this aircraft, and what is the velocity with which this aircraft is moving, which is nothing but v infinity. So can I say the thrust power on the aircraft, the thrust power which is available with aircraft, will be equal to the force which is equal to, let's say, thrust we write it by T. Okay, so power will be thrust multiplied by V infinity. I hope everybody is understanding. Okay, so the thrust power which will be available will be thrust multiplied by V infinity. Okay, now this thrust power is developed by what? This thrust power is developed by your gases which are moving, or the jet which has produced this thrust. So now we need to calculate what is the power, or what is the energy given to gases. So let's say energy provided to gases what is the energy provided to the gases or air? So again, now I will draw the vehicle again, and then we will see what are the power provided. So let's say this was your engine, okay, and in this engine you have your air which was moving in. Okay, so this is your engine where you have your air coming in with a velocity v infinity. Okay, now what happens is you provide certain energy to this air. Okay, and when you provide this energy, this air starts moving out with a velocity that is, let's say, v exit. Okay, so can anybody tell me what is the energy that has been provided to these gases? Can anybody tell me what is the energy? So you see, it was coming in with certain mass flow rate, let's say mass flow rate of air, and it is going out mass flow rate of air. We can consider mass flow rate of fuel also, because in the total energy it will be accounting, but generally mass flow rate of fuel will be much smaller as compared to the mass flow rate of air, so we are going to neglect it. Anyways, we are going to neglect it. So what is the total kinetic energy with which these gases are moving? So you see, energy provided to air or gases, ठीक है, energy provided to air or gases, ठीक है, can I say energy provided to the gases would be equal to final kinetic energy, ठीक है, minus initial kinetic energy. Okay, though this expression would vary slightly for jet engines, propeller engines, everywhere. This will vary. Why it will vary? Because the gases which are coming out of here, in case of a jet engine, they will be having a higher temperature also. So that energy which has gone, which is going out with the temperature, where is that energy? So we actually take care of that in case of the Brayton cycle efficiency. But let's say we want to keep it very simple. Okay, if there is only air which is getting energy, so what is the change in energy of the air? That is the power that you are providing. So if we are considering only air, then you can remove this mass flow rate of fuel. Okay, so in case of jet turbojet engine, slight difference will be there. Okay, but let's understand very basic principle first, then we will go to complexities. Okay, so here mass of air is entering with v infinity, and you provided energy. Somehow you accelerate this air like in a turbofan or turboprop, and the exit is moving with a velocity v exit, and mass flow rate is mass flow rate of air. So can I say the energy provided to gas or air would be equal to half of m dot air into v exit square minus half of m dot air into v infinity square? Yes or no? So you say this is the kinetic energy which has been provided. Okay, so now let's see, when you provide this energy, how much is the thrust generated by this vehicle or whatever the engine which is available over here? Thrust generated would be equal to, so if you see the thrust, okay, thrust generated would be equal to mass flow rate of air multiplied by v exit minus v infinity plus p exit minus p infinity into area exit. This is what is the thrust generated. Okay, so you see the thrust which is generated is over here, and the energy that you are providing is over here. So can we calculate what is the propulsive efficiency? When we talk about the propulsive efficiency is defined as thrust power. How much is the thrust power that has been generated by the air divided by the energy, propulsive energy, or the energy imparted to air. ठीक है, energy imparted to air. Okay, so if we calculate for a very simple case, which is over here, okay, in case of air getting accelerated, let's say in case of simple turboprop or turbofan engine, so the propulsive efficiency propulsive can be written as thrust power. Thrust power is thrust multiplied by V infinity divided by energy imparted, that is half of m dot A. This will become V exit square minus V infinity square. Okay, so if you see m dot A half will be common, V exit minus V infinity square. Okay, is it clear? Now, what is the thrust power? Thrust power is, you have already seen, it will be mass flow rate of air multiplied by V exit minus V infinity multiplied by V infinity divided by half of m dot air into V exit square minus V infinity square. Okay, so now you can simplify this. Mass flow rate of mass flow rate will cancel. This 2 will go up. Okay, so propulsive efficiency can be written as 2 multiplied by V infinity multiplied by V exit minus V infinity divided by V exit square minus V infinity square. So you see over here V minus V infinity, here V square minus V infinity square. So when you simplify this, you will become 2 into V infinity divided by V exit plus V infinity. This is what is the most simplest form of propulsive efficiency. So you see propulsive efficiency is equal to 2 times V infinity divided by V infinity plus V exit. This is very powerful relation. It tells you whatever is the energy that you are providing to the gases, how much of the energy has propelled you forward, how much of the energy has been converted into the thrust. Okay, now you see we make use of this propulsive efficiency to calculate different designs of aircrafts. Okay, so how do we define, how do we use this equation? So let's understand the concept of the efficiency variation with V infinity and V exit. So let's say if I want to draw my graph for different V exit and V infinity conditions. So let's say efficiency, and this ratio is, let's say, V infinity divided by V exit. Okay, so let's say I have a certain condition. What I'm going to do is we are going to draw the graph between V infinity and V exit and efficiency. So you see there are 3 parameters that are going to vary. Efficiency, which depends on V infinity and VE. So whenever we are drawing a graph, generally we have to vary only one parameter. So this is a 2-dimensional graph. So if you have to vary only one parameters, either you can fix V infinity or you can fix V exit. Okay, but we are going to fix V exit because generally that is what is mostly fixed. Okay, V exit is what gets fixed because you are providing certain energy, and when you provide certain energy, the air which is coming out moves with certain speed, though ideally speaking it will not be also same. Okay, but we will see how does the efficiency vary first, and then you can see all the permutation and combinations. Is it clear? So if we have V fixed, now you can say that V infinity varies from, let's say, 0 to I am taking only simple case where this is V exit. Okay, though V infinity can vary, V infinity can go much higher than V exit also. It can go, in case of rockets, it goes beyond the V exit also. Okay, but we are going to see over here only for the engines which are naturally breathing. We are not going to see rockets over here because the principle in case of rockets is slightly different. Okay, so this equation that we have derived is basically for the gases or the air which is moving out. We have not derived it for the rockets. So this is mostly for air breathing engines. So if you see air breathing engines, so let's say when velocity is equal to 0, V infinity is equal to 0. When V infinity is equal to 0, what will be thrust? Thrust, if you see, thrust will be equal to mass flow rate of air into V exit. And you see, this will come out to be maximum. Thrust would be maximum, very high. This will be roughly maximum. If VE is fixed, this thrust will be maximum, because in case of naturally breathing engine, this is what is condition which is called as at sea level or in stationary condition. So generally in stationary conditions, this is one of the thrust. But again, if you see, the thrust is not only a parameter of VE, it is also a function of mass flow rate also. So mass flow rate is again rho into area into V infinity. Okay, so there will be one more parameter which will be coming over here. So it is not as simple as that. Okay, but again I am saying ki we are not going to make, or we are not going to measure what are the different parameters which are varying. So first we will see the variation with respect to V infinity and V only. So at V infinity equal to 0, what will be my propulsive efficiency? You see, the propulsive efficiency will be equal to 2 into V infinity divided by V infinity. So this will become 0, this will become 0. So this quantity will become 0. So generally the propulsive efficiency is 0. You start from here. Okay. Now you are increasing, propulsive efficiency is 0. Now you are increasing, let's say V infinity becomes 0.1 times V exit. Okay, so in that case, efficiency propulsive will be 2 into 0.1 divided by 0.1 plus 1. So 0.2 divided by 1.1, 0.2 divided by 1.1. This will be roughly around 18-19%. Okay, so let's say this is 0.1. Your efficiency is coming out to be 0.2. Okay, I think I have drawn this much higher. Let's draw it 0.2 such that the maximum efficiency is around 1. Okay, so this is at 0.1. 0.1 efficiency is 20. Now let's go to the case where this becomes V infinity is equal to 0.2 V exit, and from this efficiency propulsive will be 2 multiplied by 0.2 divided by 0.2 plus 1, that is 0.4 divided by 1.2. You see, this efficiency will be around 33%. 12 into somewhere around 33%. So at 0.2, now the efficiency would be slightly lower. Okay, 18 into 36, or what I can do is I can draw it slightly higher so that you see the curve. You see the actual curvature. So this will be 33% over here. Okay. Now as you increase, you see that at 0.5, V infinity is equal to 0.5 V exit. Propulsive efficiency is 2 into 0.5 divided by 0.5 plus 1. That is 1 divided by 1.5. This is 0.66. So at 0.5, you have achieved roughly efficiency of 66%. And finally, when you reach 1, when you reach V infinity is equal to 1 times V exit. At that time, propulsive efficiency will become 2 into 1 divided by 1 plus 1, that is 100%. So you see, the curve becomes something like this. Okay, so the curve becomes something like this. This is what is the propulsive efficiency. This is how the graph of propulsive efficiency comes. So higher is the matching between V infinity and V exit. Higher will be efficiency. Okay. So you see now we will see the two cases of, we will discuss the two cases of turbojet engine, and we will discuss the case of turbofan. Okay. So turbofan. Okay. So in case of turbofan engine, you see that the gases which are coming, or the air which is coming in, it enters with V infinity and it exits with V exit. So for very high efficiency, what do you want? You see that for high efficiency, you want V infinity or V exit to be slightly as close as V infinity, or V exit to be slightly higher. Okay. If the ratio V infinity by V exit close to 0.9 or 0.95, you will see the efficiency will be very high. This is the region where we want to operate. This is the region where we want to operate. Why this region? Because you see the propulsive efficiency will be very high in this range. So if you want this to be very high, then your V exit minus V infinity should be small. For very high propulsive efficiency, V infinity minus V exit should be small. But what is the problem with this V exit minus V infinity being small? You see, the thrust developed in a propeller engine was mass flow rate of air multiplied by V exit minus V infinity. So now you see, when you have mass flow rate of air multiplied by V exit minus V infinity, if this becomes small, you see thrust becomes small. Thrust gets smaller. So from here you see that thrust and propulsive efficiency, they are not going hand in hand. If you want propulsive efficiency to be higher, the thrust will go down. Okay. So they are basically inversely proportional. Thrust is inversely proportional to propulsive efficiency. If this is higher, this will become low. If this is low, propulsive efficiency will be low at what condition? Propulsive efficiency will be low at condition where V exit and V infinity are very different. And where does that happens? It happens in this range. So as I already told you, over this condition, thrust would be maximum. Why? Because thrust is V exit minus V infinity. So you see that this becomes high, the thrust becomes high. So they does not go hand in hand. And this is the reason why you see that turboprops, they have a much higher efficiency when they are going close to V exit, but at that time they will lose thrust. Okay. So now if you want to maintain that thrust, what you have to do? So to maintain the thrust, what you have to do? So you see that thrust has two components, mass flow rate of air multiplied by V exit minus V infinity. So what we actually do is we reduce this quantity. We try to reduce this quantity V exit minus V infinity so that our propulsive efficiency could be high. And we try to increase mass flow rate of air. And from this, how do we do? So mass flow rate of air should be increased. Okay? And when you increase the mass flow rate, you see mass flow rate is nothing but rho into area into velocity. Rho into area into velocity. Velocity is nothing but velocity of. So generally this remains constant. This V infinity also, for the time being, we will keep it equal to V exit. So you see rho becomes constant, V infinity becomes constant. You are left only with a parameter which is called as A. So what we do is we increase the diameter of the fan. So we increase diameter of fan. So when you increase diameter of fan, you see that fan will absorb, or fan will suck in more air. So when fan sucks in more air, more amount of mass is sucked in, and when more amount of mass is sucked in, the thrust is maintained. That is what is actually called as high bypass. If you see, they call high bypass fan engines or fans, high bypass fan. High bypass fans, they have a very large diameter of the fan. They are making the engines to be very big. GE9X is going to be one of the biggest engine with a fan diameter of 134 inches. Okay, and this is what 134 inches, even bigger than this. Okay, so you see, this is what the airline industry is doing. So to improve the efficiency, maximum efficiency that they have, what they do is, so propulsive efficiency will be higher. So what they are actually doing is they are bringing V exit close to V infinity, and they are increasing mass flow rate of air. So you see, again, there are a lot of parameters. Still, it is not as easy as I say. Okay, when we will discuss the turbofan in detail, how is the thrust developed, how much is the thrust developed, we are going to calculate the actual thrust developed. At that time, we will see there are different parameters. Okay, so we have seen that the propulsive efficiency in case of turbofan engines, in case of turboprops. So turboprops and turbofans both have almost the same efficiency parameter. So efficiency, propulsive efficiency in both the cases will be equal to 2V infinity divided by V exit plus V infinity. I hope it is clear to you, clear to everyone. Again, for the cases of turbofans, turboprop, turbojet. Now let's discuss what happens in case of turbojet. Okay, so turbofans we have discussed, but for turbojets, okay. Now if you see turbojet engines, the propulsive efficiency would be, the propulsive efficiency propulsive will be thrust multiplied by V infinity divided by the energy that you are imparting, mass flow rate of air, V exit square minus V infinity square. Okay, so in case of a jet, turbojet engines, again, the thrust that you have to calculate would be calculated based on the first equation that we have got. So propulsive efficiency is thrust. Thrust is mass flow rate of air plus mass flow rate of fuel multiplied by V exit minus mass flow rate of air multiplied by V infinity plus P exit minus P infinity into area exit. So this whole will be multiplied by V infinity divided by the energy that you are providing in case of the propulsive power, the change in kinetic energy. So this term will become mass flow rate of air plus mass flow rate of fuel multiplied by V exit square minus half of mass flow rate of air, V infinity square. But you see, in case of turbojet engine, not everything can be given to you. So we are going to assume 2-3 parameters. So if if we assume that P exit is almost equal to P infinity. So if P exit and P infinity are same, this term will go away. Generally that happens. Okay, since there is a very small thrust generated from the turbojet. Okay, so due to the pressure difference, we can remove this. Okay, and again you can assume mass flow rate of fuel is almost equal, is negligible, okay, as compared to, if it is negligible as compared to mass flow rate of air, then you see you can remove this mass flow rate of air and mass flow rate of fuel terms also. And if you do these two parameters, then again the propulsive efficiency, the parameter of propulsive efficiency would again come out to be 2V infinity divided by V exit plus V infinity. The same terms will come out because this term will go away. Okay, once this term is gone, a mass flow rate of fuel into V exit minus V infinity. So a mass flow rate fuel will also go away. So once these terms go away, you see the propulsive efficiency would be almost equal. So you see more or less this propulsive efficiency is almost equal to this. But now in case of a turbojet engine, so for turbojet, okay, for turbojets, V exit is much higher than V infinity. And when V exit is much higher, like if like the order of 2 to 3, so V exit could be of this range. V exit could be around 3 to 4 times of V infinity, even more than that. It in case of supersonic aircraft, this could go as high as 6, 7. Okay, so if that is the case, then you see the propulsive efficiency would be significantly dropping. I hope it is clear to everyone. So for turbojet engine, for turbojet engines, efficiency propulsion is very small. Okay, it could be in the range of 0.3 to 0.5. Okay, we have seen that in case of the jet velocity to be around 3 times the velocity of infinity, or the free stream velocity, then it will be lesser than 50%. Is it clear? So I hope most of you have understood how does propulsive efficiency look like. We can draw one more diagram that is generally used for comparison of different aircraft, and that is the propulsive efficiency with respect to the Mach number. Okay, so when you see Mach number, we say it is V by C. Mach number is velocity divided by C. And if you see, this velocity will be velocity of aircraft divided by speed of sound. So how does the different engines, turboprop, turbofan, turbojet engines actually reach these efficiencies? So at different Mach numbers, we can see that the engines have different sort of efficiency. So if we talk about the turboprop engines are somewhat like this. Okay, and the maximum Mach number is somewhere around 0.4, okay, 0.2, 0.6, 0.8, and Mach number, let's say 1. Okay, so turboprop engines have efficiency like this. This efficiency would be somewhere around 70 to 80%, 0.7. Okay, and as you see, they reach a certain height, they reach a certain Mach number, and after that you see that the propulsive efficiency drop. This propulsive efficiency drop because the speed of the propeller tip reaches the Mach number. Okay, and at that time there are losses from the tip, so you will see that there will be shocks generated and there will be huge loss. So the thrust would be reduced. So once the thrust reduces, the propulsive efficiency reduces. Similarly, the same turbofans also. So turbofan also, they have sort of curve like this, but there the domain is much more varied. So turbofans can show a much bigger domain. So they can go in the range of like this. So in they have the maximum efficiency very close to the Mach numbers, Mach number of 1. So their maximum efficiencies are reached at Mach number of 0.8 to 0.9. So turbofans, they run much smoother over a larger domain. They give a broader efficiency. Okay. Sometimes this efficiency could be like overlapping with over here, and it could be in this. That again depends on design to design. Okay. And finally, we see, if we see a turbojet engine, you see for turbojet engine, efficiency would be, so efficiency of turbojet, it will be 2 into V infinity divided by V exit plus V infinity. So you see, in case of a turbojet, V infinity is almost constant, and which is V exit is much higher than V infinity. So if you see over here, then this bottom parameter will be almost constant, and you see that efficiency will be directly proportional to V infinity. Okay. So in case of a turbojets, you see the curve almost goes like this. Okay. This is your turbojet. Okay. So turbojet, then you have turbofan and turboprop. So you see why most of the airlines, they have turbofan engines. You see that there are different application at based on the propulsive efficiency. So if you are operating in a range which is much smaller, so in this range where the aircraft speed is much smaller, so very smaller aircraft which are like 10 people carrying 10 passengers or 5 passengers, 7 passengers, very smaller private jets. Most of the private jet, you will see they will be having a turboprop. Why they have turboprop? Because turbopropellers have extremely high efficiencies as compared to fan and turbojet in very smaller Mach ranges. Okay. When we move to commercial airlines, you see commercial airlines which operate in the range of 0.5 Mach number to 0.9859 till 9 Mach numbers. You see in those ranges, the turbofans have a much higher efficiency. They have much higher efficiency as compared to the turboprop. They have much higher efficiency as compared to turbojet. Okay. So they are mostly used. These are commercial airlines. Okay. Commercial airlines. Okay. These are smaller private jets. Okay. And finally comes fighter aircraft, which runs at much higher speeds, close to Mach number 1 and beyond that. So you see beyond that, the efficiency of a turbojet will be much higher as compared to all the three. So for ranges which are in these range, you have fighter aircrafts. Okay. So fighters will have turbojet. That is the reason why if you see most of the fighters, they have turbojets. Is it clear? Okay. So turboprop. Turboprop is generally used for smaller aircrafts. Small aircraft. Okay. Then you have turbofan. Turbofan, they have commercial aircrafts. Okay. If you see high bypass fans would again be, they will be lying somewhere over in this region. They will not go as close to 1, but in the range of 0.9. If you compare a simple turbofan and a high bypass turbofan, high bypass turbofans would have much higher efficiency in this region because they have velocity difference V exit minus V infinity to be very less. Okay. And finally, you have turbojet. Turbojet, these are used for mostly fighter jets. Okay. Why we have fighter jets? Because in case of fighter jets, the main component of fighter jets is not efficiency. You don't want to run on efficiency when there is a enemy plane which is chasing you or enemy missile that is chasing you. So for fighter jets, thrust is the main criteria. thrust is main parameter. So we want to control the thrust. You want to have as much as thrust possible. So thrust would be maximized when V exit will be much, much higher as compared to the V infinity. Is it clear? Okay, so this is how the propulsive efficiency looks like. Guys, we are not going to talk about the efficiency of rockets, because in case of rockets, the parameters that are provided are slightly different. Okay, in the rockets we have already seen that if you see a rocket chamber would look something like this. There will be a chamber in which there will be combustion happening, and there will be a nozzle which is attached to this. So when we talk about the efficiency of this engine, you have to talk about, when we talk about efficiency of this engine, it will be only the propulsive power or the thrust power divided by energy mass flow rate of fuel multiplied by calorific value. Okay, so there will not be any Brayton cycle which will be running over here. So in case of, if you want to calculate how much is the efficiency, so that efficiency is actually calculated in terms of it is specific impulse. Okay, so we will see that specific impulse is calculated is basically the thrust divided by how much is the mass flow rate of fuel that you are providing. So this is what is actually the terms of efficiency. We will see what a specific impulse is and how does it look like, why we have to define this only. Okay, so that we will see later when we will be studying in detail the rockets. Okay, so now let's do one question on the propulsive efficiency, and then we will wrap this session up. In the next lectures, I will take. I have got few of the suggestions where most of you want lectures on centrifugal compressors. Okay, centrifugal compressor. Then you want a lecture on axial compressor. Okay, so these two lectures I will take. In fact, before taking these two lectures, in one lecture, which will be slightly longer duration, around 2 hours, we will be discuss what is the governing equation, which is called as Euler's equation of turbo machinery. So we will discuss, first of all, we will develop this Euler's equation. Then in one of the lectures, we will see what are the different components of Euler's equation. And once we have discussed the Euler's equation, then we will apply that Euler's equation to centrifugal compressors and axial compressor. It is very interesting topic, and I generally teach it from very basic. First, we will develop the Euler's equation. First, we will understand the Euler's equation, and once you have understood the Euler's equation, drawing the velocity diagram for axial compressors, drawing velocity diagrams to calculate power in centrifugal compressor, pressure developed, everything would be much easier. Okay, so we will discuss all in the coming sessions, but let's do one question on the propulsive efficiency first. So air enters compressor of a Brayton cycle. Oh no, not this. Air enters a turbofan moving at a velocity of 200 meter per second and exits the fan at a velocity of 290 meter per second. It says find the propulsive efficiency of the fan. Okay, so we know that propulsive efficiency of a fan can be defined as 2 into V infinity divided by V exit plus V infinity. So it is given that your fan is, or the engine is, aircraft is moving at the velocity of 200 meter per second. So 200 divided by V exit is 290 plus 200. So this is 400 divided by 490. This will come somewhere around 81 or 82%. So propulsive efficiency would come out to be 0.400 divided by 490. It is 0.816. So 81.6%. So 81.6% of the power which have been given to the propeller, that has been utilized to develop thrust. So now if you see, you guys might be wondering that what happens to the remaining energy? Where is that remaining energy going? Where is the remaining 18% energy going, which has not been imparted to the thrust? So you see, guys, I'll tell you where the energy is going. So let's say these are the air particles which are present in the atmosphere when one of your aircraft is moving. So you see, the energy which is available with this aircraft, they are energy available with the particles which are there in atmosphere. They have their velocity to be 0. They are not having any velocity. They are just sitting over here. Now you see one of the aircrafts, it enters this space and it takes in air and gives certain thrust to the velocity, uh, gives certain velocity to these particles. So you see, once this aircraft has come over here and it has moved. Now, once this aircraft has moved out of these particles, you see the particles which have passed through this aircraft, they will have a velocity which is going in this direction. And the energy that is available with these particles is that remaining 19%. 19% of the energy is available in form of half of m dot into v square. So earlier these particles were having zero kinetic energy. Now these particles are actually moving backwards. Is it clear? When this aircraft has moved out, it has thrown particles at velocity v exit. And this aircraft was moving in this direction with velocity v infinity. So you see the particles, air particles, they have actually received a velocity which is half of m dot into, you can say, v exit minus v infinity square. This sort of energy they have got it. Is it clear? They have got this energy, and this is what is the 19% which you cannot convert into the propulsive efficiency. The remaining 81%, this 81% energy would be utilized for propelling the aircraft through air. So when air is passing over this aircraft, you will see there will be different drags. There will be friction drag over here. Okay, there will be other like eddy viscosities and everything will be present. There will be pressure drag from here. When the nose of the aircraft, you see, there will be certain compression happening. So 81% of the energy would be used to overcome the drag, friction, everything. And remaining 19% energy is provided to these air particles in pushing backward. So now I hope everybody understands where is the actual energy going, which has been provided by fuel. Understood? So if you have understood, guys, then I'm sure you might have liked today's lecture. So today we discussed about propulsive efficiency. In my first lecture, one of the student had said, sir, let's discuss on certain performance parameters. So guys, this is one of the performance parameters that we define for engines, aircrafts, mostly which are turbofan, turboprop, turbojet. Okay, so this is one of the parameters, one of the most important parameter we have discussed. In last lecture also, I had asked which all topics you want me to teach. And guys, you have given your feedback about the compressor, so axial compressor and centrifugal compressors. So certainly I will take those two lectures, those two topics. But in case if you want any other topic you want me to teach over here, then do let me know in the comment section and I will take that topic. Okay, thank you. So I hope you are enjoying these lectures. Okay, do let me know how do you find these lectures. Okay, thank you.